Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to taking the class of Embedded System Design. The code name is EC703B and this is the lecture number 50. Now that what we have discussed in the previous lecture is what we have described in the previous lecture in lecture 14 is that we have described about the OS. How OS work, what is the significance of operating system, what is a real-time operating system, and in that lecture we have described about the different kind of operation that a OS must conduct, what is a boot program, how it works as as a supervisor mode, how it works as a user mode, how it load the computer, how it initialize the computer, and how it works with system calls, interrupts and handling. So all these are things that I have already discussed in this in the previous lecture. So from this lecture I am going to describe this lecture, this specific lecture will be the continuation of the previous lecture. So let's begin with the lecture. In this lecture, in this slide, what we have here is called a system call. So what is a system call? A set of interfaces to interact with hardware devices such as the CPU, disks and printers. So a system call is a set of interfaces to interact with the hardware devices such as the CPU, disks and the printers. So if we have to work with the disks and the printers, what we use as a system call. The advantage of system call is freeing users from studying low-level programming. It greatly increases the system security, and these interfaces make programs more portable. So let's go to the next slide. So let's go to the next slide. So the system call. How the system call works. So a set of interfaces to interact with hardware devices such as the CPU, disks and printers, and these are the advantages that I have already described in the previous slide. So this is the specific pictorial diagram of the system call, how it works. So first the system call interface, where the user application are latch with the system call interface, and this is the implementation of open system call and return. This is the user mode, this is the kernel mode, and this is the user mode and this is the kernel mode. So this is the pictorial depiction. And for a OS programmer, calling a system call is no different from a normal function call, but the way system call is executed is way more different. So let's go to the next slide. The calling sequence of a system call. The first one is the user processor, the user process executing. Next one, the call system call. Now this is the trap mode bit is equal to 0. It will execute the system call. After we calling the system call, the kernel will execute the system call, and after the end of the system call, the return mode bit will be 1. So it will return to the return. It will return from the system call, and it will goes according to it. It means in case of system call, the same thing will happen. Suppose there is a process that has been going on in OS. So now in a user process, the user process executed, it will cause the system call. Okay, and the trap mode bit will go to the 0, and in the kernel the system call will be executed. After the execution completed, the return mode bit will be 1, and that control of that system call will be returned back from the system call as the user process will continue. So this is the time, this is the space where the kernel will execute the system call. After after this system call execute, it will return to the system. It will return from that system call. It will return to the user process. So this user mode bit will be 1 and kernel mode bit will be 0. Logically, the system call and the regular interrupt follow the same flow of steps. The source input-output device versus user program is very different for both of them. Since system call is generated by user program, they are called as soft interrupts or traps. Basically, the trap bits execute the system call, but in case of interrupts, it has a very different functionality. So let's go to the next slide. Now so there is the end of the system call. Now from this slide we are going to discuss what is a task is. A task is an individual execution unit of an application. A task starts with some parameters or inputs. It does a specific job assigned to it. It either runs forever in a loop or terminates. It communicates results to other tasks of the application. And the different types of tasks that we will encounter will be preemptive, non-preemptive, and round robin. These are the very specific tasks, and we are going to discuss in the upcoming lectures and even slides. So this is the task, and let's go to the next slide. So the application of task is any application can be split into a number of tasks. That's the important point. Any application can be split into a number of tasks based only on parallel operation possible for the application. If there is a possibility of an application which can be operated parallel, it means simultaneously in the very same time frame, there is a possibility that parallel 3-4 operations is going on, then the application can be split into a number of tasks. So this is the one fact. Suppose for example, a car can have a different tasks for controls, such as for the following: driver, gears, windows, temperature, door lock, theft lock arm, brakes, accelerator, airbag, accident emergency, ignition, fuel tank, brake oil. So all of this operation or the application can be handled simultaneously at the same time frame. Within the same time frame, we have to handle all these parameters. So these are the specific tasks of a application. Now the whole application is to drive a car safely. Now that application has been split into various number of tasks, and these tasks can be performed simultaneously. So this is the basic example of a task, how a task is happened, and what is the specification, or the significance of task. Now these parts can run in, that's what I have already discussed, that these parts can run independently. However, at times they will need to communicate with each other. Alternatively, there can be a master task supervisor these tasks, which creates, manages, and destroys. Suppose there is an application we need to consider. Now this application has been split into various number of tasks. Now suppose this task has been happening parallelly with 3-4 tasks has been happening, and at a point that we need to communicate between all these 3-4 tasks, because the whole propaganda of this task is to continue with the driving of a car safely. So all the windows, temperature, the door lock application, the brakes and accelerator application, the airbag, accident emergency application, all these tasks are being collaborated in a specific application. The application, the motto of this application is to drive a car safely. So this is the same process in which also the PC works in that way. Okay, so let's go to the next slide. The next part is what's the difference between a task and a program. Now this is a program where we have initialization, such as where suppose this program is int global1 is equal to 0. We have initialized a value 0 to the global1 variable. We have initialized a value global2 integer global2 variable. The value will be 0. Now the void do something condition has initialized another variable, that is a local variable, that is local2 is equal to 5. We have initialized we have assigned a value 5 to the local variable local2. Now now we have operated on the local2 with an increment value. Now after the end of that void do something program, the int main program will be character multiply with local1 is equal to malloc 100. So this is a specific program, and this is a process where the whole process has been defined or has been split into different kind of tasks. So what we have has here, is that a task is a running instance, whereas a program is just the code which resides in a primary or secondary memory. Now this program, probably it will be residing in a secondary or primary memory, and it will be activated when it has been fetched. Now after fetching a program, it will be decoded, and the instructions that has been occurred according to the program, and the data will also be fetched according to this specific program. So but in case of task, it's a running instance where a program is just a code, and a program is a passive entity because we need to initiate that program. Suppose there is a program, it could be reside in a memory, in a secondary memory. Now until and unless we initiate that program or we fetch that program, it is basically an inactive thing. So that's why it could be said is a passive entity. Program is a passive entity, such as file containing a list of instructions stored on a disk, whereas a task is an active entity with a program counter specifying the next instruction to be executed and a set of associated resources. Set of associated resources will be allocated to this program, to the specific next instruction, and the program counter specifying the next instruction to execute. So this is an active entity. The task is an active entity. A program gives rise to one or more active tasks. When an executable file is loaded into a main memory and execution of the task begins. So this is the process, and this is the local 1, local 2 stack variable. This has been memory allocated, and this is the global variable that has been also assigned to a memory location. Okay, so let's go to the next slide. So this is the description of a task states, how the task states work. Now suppose this is a new task that has been admitted to the ready state. Now this ready state will be in a running state until and unless there will be an interrupt. Suppose the ready state and the relationship between the ready state and the running state will be the introduction and the intrusion of interrupt signal. Suppose there is an interrupt signal has been invoked. So the state which is in a running, the task which is in a running state will be, if that input output event happened, what will happen? It will go to the waiting state. Okay, so after the input output of the event completion, the waiting state will be again go to the ready state, and after that it will again go to the running state. So suppose there is a task which is in a new task which has been initiated. After the admission, it will be initiated, it will be in a ready state. So the next step will be, if there is no interrupt, it will be just jump to the running state, and after the task completed, it will go to the exit state and it will be terminated. Now suppose during a task which is in a running state, suppose there is an interrupt signal that has been occurred or invoked. So what will happen? The running state will be go to the task which is in a running state. It will go to the waiting state. And after the completion of the interrupt signal, after the interrupt signal has been occurred, if the processor after the interrupt signal occurred, the processor will handle the interrupt signal. If there is a important execution that needs to be done, important operation that needs to be taken place, it will take place. And until and unless the interrupt signal unless the interrupt signal dispatched, that task will be in the waiting state. After the interrupt signal, after the completion of the interrupts instruction, the task which is in a waiting state will again jump to the ready state, and after that it will jump to the running state, and it will according to its due course it will end and terminate. So that what I have described here has been written here also, that a task goes through a multiple states ever since it is created by the OS. New, the task is being created, that I have already said, and the running is the instruction are being executed. Waiting, the task is waiting for some event to occur, and ready is the task is waiting to be assigned to a processor. This is the ready process, and in the running state it has been executed, and ready state it has been waiting for the waiting to be assigned to a processor, and the terminated state will be the task has finished execution, so it will be in a terminated state. So this is the different kind of task states. So let's go to the next slide. And the task descriptor. To manage tasks, operating system kernel must have a clear picture of what each task is doing. Task's priority, whether it is running on the CPU or blocked on some event, what address space has been assigned to it, which files it is allowed to address, and so on. This is the role of the task descriptor. Usually, the OS maintains a structure whose fields contain all the information related to the single task. Okay. So, task descriptor, what is all these things really means is that to manage a task, operating system kernel must have a clear picture of what each task is doing. Task's priority, that which task has to be performed first. So the priority list should be maintained. Whether it is running on the CPU or blocked on some event, it's also been tested, because in the earlier slide that we have seen, that suppose this is a new state where the task has been created. After that, it has been admitted to the ready state where it has been waiting. It has been waiting for it has been waiting to be assigned to a processor. Suppose that task has been assigned to a processor and it has been running, it has been executed. Now suppose if the interrupt signal occur during the execution of that specific task, what will happen? The whole task will be go to the waiting state. Okay, so it will wait until the interrupt signal has been properly dealt with. If some event need to be occurred, it will occur, and up to that time the whole task will be in a waiting state. After the completion of the incident which has occurred, the task will move from waiting state to the ready state. So after and in the ready state, it will again be waiting for that specific it will be ready to be assigned to the processor. So after few moments, it will again go to the running state, and after the completion of the running state, it will again jump to the terminated state. So that what we have described here, that the same there, whether it is running on the CPU or blocked on some event, it is depending upon whether it is running on the CPU or blocked on some event, it is need to be to manage it. So this is the way you should manage the task, and what address space has been assigned to it, it is also being need to be dealt with, and which files it is allowed to address, and so on. All these things needs to be to manage a task. We need to know what address space has been assigned to this task, which files it has allowed. It means the which resource needs to be allocated to this specific task is also need to be managed by the processor. And this is the role so these are the role of the task descriptor. These are the role of the task descriptor, that to understand the task priority, whether it is running on CPU or blocked on some event, it also need to be dealt by the task descriptor. What address space has been assigned to it, which files it is allowed to address, and so on. Usually the operating system maintains a structure. Usually the operating system maintains a structure whose fields contain all the information related to single task. Usually the operating system maintains a structure whose field contains all the information related to the single task. This is the important point, need to be remembered. Let's go to the next slide. So these are the task descriptor fields. The information associated with each task is the task state. The task state. This is the task state. The pointer, the program counter. So it will address the next instruction to be executed. Task number, how many numbers of tasks are being dealt with, or how many numbers of tasks are being parallelly being working on, how many it needs to be remembered. So this is the pointer, and this is the program counter. Okay, this is the register where the next task which the task needs to be executed will be stored in the register, CPU register. And this is the CPU scheduling information. The CPU scheduling information is also important, because scheduling the number of tasks, the listing of number of tasks is a very important factor, because without the proper scheduling information, we can't perform the task simultaneously. So it is an important point. And the memory management information, this is also need to be dealt by the task descriptor. So, and another one is input output status information. It is also being dealt by the task descriptor. And this is the list of the open files. These are the pictorial depiction. Let's go to the next slide. And another thing that is need to be understood here is the context switching. So how it works, that is need to be understood. What has been written here, that switching the CPU to another task requires saving the state of the old task and loading the saved state for the new task. If I read again, what it means is switching the CPU to another task requires saving the state of the old task. The old task, it means this task which is running, to stop that state and send it to the waiting state. That is the one of the important thing of the switching. So switching the CPU to another task requires saving the state of the old task and loading the saved state for the new task. So second one, the time wasted to switch from one task to another without any disturbance is called the context switch or scheduling jitter. So now we're going to understand how it works. Now suppose this is the process P0, this is the operating system, this is the process P1, this is the process. Now suppose this process P0 has been executing, so it is in a running state. So if we just go back to, now the process P0 is in a running state, and suddenly interrupt or system calls. Suppose there is an interrupt, suppose we have used a printer, suppose we are doing a task and we have put the jack of the printer and we started to print. So suppose there is an application that has been installing, or we are installing a application, and suddenly we need to do a printing job. So what will happen? The installing job, suppose that job is process P0. So the execution of that process P0 will be go to the waiting state. And what will happen? The interrupt system call, that this process will save state into the PCB. It will be in a save state. Okay. And the reload state from PCB, save state into the PCB 0, and the reload state from PCB 1. So it goes to this point. It means the process P0 executing. Okay, so suddenly there is an interrupt system call, but this process is not executing at the time because it is in idle state. So what will happen, that executing the state which is in a running state, the processor will go to the hold, sorry, the task will go into a hold position. The interrupt system call has been appeared, that save state into the PCB 0 and reload the state from PCB 1. Okay, it has been saved. Okay, sorry, it has been in a save state into PCB 0, then it is in a reload state from PCB 1. Okay, so up to that this is in a idle position. After the reload state from PCB 1, that process P1 will start executing. It means it has been go to the running state. What it really means is that in process 0, which is in a running state, after the interrupt calls, what will happen? It will go to the idle state. It's basically stopped. Now what will happen? It is in a running process. So from that running process, we have to send that process, we have to save that state, and we have to reload the state from PCB 1. Okay. Okay, so after this reload state from the PCB 0, the process P1, which is need to be executed, will start executing at the running state. And after the execution will completed, what will happen? Now what will happen? This state is go to the save state into PCB 1. Okay, and after a few moments, this process which is being idle up to this point will, after the reload state from PCB 0, it will again start. It means basically it is in a PCB 0 state. So we first, after the interrupt system call, the process P0 which is running will go to the save state, and the reload state is from the PCB 1. After the reloading of the process P1, it will start executing. After the execution has ended, what will happen? It will save the state into the PCB 1, and it will reload the state from the PCB 0, which has been saved in the earlier moment. So after the reloading of the state from the PCB 0, again the process P0 will start executing. So the whole process is known as the context switching. So now we will end the lecture. we'll end this lecture, we'll conclude this lecture here, and we'll start understanding other things from the next lecture. Okay, thank you.